So yeah, I already presented some of this work in different frameworks. So today I thought I would include new materials that will be maybe more interesting specifically to the ANSS community, and especially the monitoring of ANSS performance metrics, but also the use of machine learning algorithm to better monitor data quality. So today's presentation is going to be about BATS, as Mary said, which is a consolidated solution for monitoring the all state of health information from the BSL operational systems. That's really a team effort. A lot of staff and students have been participating and are still participating in from the Berkeley Seismology Lab, are still participating in the development of BATS. But first, maybe let's start with what BATS stand for. BATS stands for Berkeley Analysis Tool for State of Health. And so before we had BATS, we had in fact quite a number of tools that we were using to monitor different parts of our systems, and that were progressively integrated. And so when one staff wanted to troubleshoot an issue, whether it's at the networking level or station level, there was a need to log into different tools to try to collect all the necessary information to be able to troubleshoot a specific issue. And in addition to that, there was sometimes a lack of coherency between the information that was being received from the different tools, because these tools were not reading the information at the exact same place, and that was making troubleshooting even more difficult. In addition, some of these tools were not open source, they were hard to maintain, and most use, at the time we started that project, obsolete technologies. In addition, some components of our system were not monitored adequately, and some were even not monitored at all. And this was especially true for the quality of our data and products that was mainly monitored manually, but not through automatic checks. And finally, it was also, we had all these different tools to monitor these different system components, but it was not so easy to get a good understanding of the overall system performance. For example, our capability to deliver data and products to the relevant stakeholders, or for example, in the framework of our earthquake early warning system, what would be the performance of that system if there would be an earthquake happening right now, given the status of our network, telemetry, data center, etc. So we defined, when we defined the project objective, of course, one of the main objectives was to monitor all the BSL operational system through, if possible, the same technical solution. And that would include, of course, our large network of seismic and geodetic stations, our new DAS infrastructure, telemetry between the station and our processing centers, our real-time data acquisition system, our real-time and post-processing software for earthquake monitoring, our data center, our underlying IT infrastructure, the MyShake application, which is developed and operated and maintained by our lab as well. As I mentioned earlier, the quality of the BSL data and products for ANSS application, and the performance of the earthquake early warning system we are part of. And so we started thinking about the main design requirements we wanted for our system. I will not list them all here. I just wanted to highlight a few of them that I think were that are the most relevant for today's presentation. One was, as I mentioned, to have a single user interface to monitor all system components. That was key in our design. Also, the use of open source software in order to build on existing state-of-the-art solution and then minimize development time. We didn't want to reinvent the wheel. We didn't want to redevelop what already existed out of the shelf. We also wanted to build a modular, flexible, and easily expandable system. We know that our system are expanding. We keep adding station. We keep adding monitoring capabilities. So we wanted to have a flexible and easily expandable system. And we also wanted to clearly separate the data, application, and presentation layers. That was one issue with the tool that we used to use to monitor our network of station. This was a full package, and it was very difficult to implement changes. And if we wanted to replace that tool, we had to replace all the layers at the same time. We didn't want that to be the case in the future. And finally, also, as I mentioned in introduction, we wanted also to really define a single source of truth for all the displayed information. So if one information would be displayed even through our different dashboard or different parts of the monitoring system, it had to come from a single source and not from different databases that would have to be maintained, and that could potentially not be all up to date and contradict one another. Okay, one main piece of that system is the solution that we use for the presentation layer. That solution is called Grafana. That's the only part of our solution that I will talk a little bit about in more detail, because we spent quite a lot of time exploring different solutions that were available in the market. And at the end, after a period of testing, we really saw that was the solution the most adapted to our needs. It is also a solution that has been already chosen by other agencies that monitor a very large network of stations, such as, for example, the AFTAC or the NAC program, the CTBTO, etc. And one reason, I mean, some of the reasons for which we decided to choose Grafana, the first one was the modularity. So really the possibility to, even on a single web page, be able to pull information from many different types of databases, many different sources, and you see here such as Postgres, Timescale DB, MySQL, etc. Also the supportability, the fact that it can run on multiple operating systems, and also something that was very important for us, to be able to run on cell phones, especially for field engineers or people who are on duties at night or during weekends. Usability, we wanted to have a set of core dashboards that everybody would have access to, but we also wanted everybody at the BSL to have the possibility to start his own dashboard very quickly if he would be interested in troubleshooting an issue, and being able, to link some database field and display, to the dashboard and display that information very fast and in a convenient way for troubleshooting issues. Performance. We have a lot of data. We wanted also to be able to display very long time series, even for several months, very rapidly be able to display data from our data center, for example, over a long time period, and not having to wait for this information to be displayed. Maintainability is also a big point, because we wanted to make sure that the solution we choose will be maintainable on the long term, and also will offer all the option in terms of assistance and API to interface with the different part of the system. And finally, scalability. We know that our system are expanding. We know that we're also expanding our monitoring, so we wanted a system which can extend quickly and fast. So that's really the solution we have chosen for the presentation layer, so for the display of the information. But of course, that's only one part of the solution. So as you can see on the right of the diagram, I don't know if you see my mouse. Do you see my mouse? Or yes? No? I don't know. So
yeah, we can see. I can
yes,
see the
we
mouse.
can see a mouse.
Perfect thing. So on the right side of the diagram, you see the main users that we thought about when we designed our system. So the first one is the sysadmin team, and that support all the underlying IT infrastructure. We also thought about the team that operate the network and troubleshoot the network of station and the telemetry. all the field engineers also that do both remote and on-site, so at the site, at the station troubleshooting. And as I mentioned, the possibility to access that system through cell phone. And finally, all the team which is in charge of reviewing the data and products that we produced, and make sure that they also have this, the information they need available to them. So mainly through a unique graphic interface. So as I mentioned, through Grafana, and of course, so Grafana then will connect to different databases in order to display that information. So the first thing we wanted is not to reinvent the wheel. We already had at our data center, we're already storing a lot of waveforms from the raw data, the raw seismic and geodetic data, but also a lot of state of health channels. So we wanted to be able to display that information directly without having to store that in another database. And we managed to do that through a Flask API that allows connecting to our data center and display that information directly in Grafana. For the rest of the system, so we are storing this information in different type of databases. Some already existed, some are new ones. Again, we are mainly using two types of databases, Postgres and Graphite. For example, at the station level, we develop new data collection agents for our power system, communication system, and we are putting that information in those databases. Same with our AQMS, so both real-time and post-processing earthquake monitoring system, putting the information from those systems into those databases, data quality. And we were already using Nagios for alerting, mainly for the IT infrastructure and our EEW system. And that information was already available within Nagios. So we just decided to use Pandas to be able to import that information into those databases and be able to display it with Grafana. So in summary, we wanted to make sure that we tackle the needs of all our operational team through a single interface. But of course, the system in the backend is a little bit more complex than just the user interface itself, Grafana. But the great news for us is that in fact we didn't have to touch to the existing system like the Nagios piece or the data center piece, and we could just pull out information directly from these data sources. In terms of IT infrastructure for that system, we wanted also this system to have a very high availability. Again, we wanted an operational tool. We didn't want to have a tool that will be half in development and that will not be available all the time to our users. So that's why we came up with like this standard like dev, test, and production environments. We even have two production environments, so we can switch from one to another whenever we push new operating system or software updates, for example. So that will ensure that we have an extremely high availability for our production system. And then for developers or people who want to play around with potentially new dashboards, we have both a dev and test environment in order also to test a new version of Grafana when they are available, new data collection agents or new dashboards as needed. So with that slide, yes, I just wanted to emphasize that we have, BATS is an operational system and with a high availability. So I think that's time for the live demo. That's always, a risk to do a live demo, so we'll see how it goes. But we have been using BATS for more than 2 years now at the BSL. We have completely retired most of the system we used to use. Our field team, network engineers, most people at the BSL use BATS now as the single source of information from state of health monitoring. So today I'll try to cover the state of health information we get from our network of stations, and then in more detail about each specific stations. I'll talk also about data quality, ANSS performance matrix monitoring, earthquake early warning performance, and also IT infrastructure. So if you give me a few seconds, I'm going to try to switch to my web browser. Can you see do you see now my web browser and BATS? Yes?
Yeah, we see it.
Perfect. So I thought I'll start with the network of station, of course, because that's, I think most of you are involved with, in some ways, with network operation. So what you see on this map is all the BSL stations that are currently operational, and the color represent the latency. This is one of the landing page, and that gives you already an overview of what can be done with BATs. So that's real-time information. This is updated every seconds as the latency. We are reading that latency from this L1Z script. You can of course zoom in, zoom out on the map. You can also here you have a table below on the right, sorry, with the different values. You can organize the station by latency. Those are the stations that are currently down. But then you see the latency for those stations. Most of those stations with very low latency, they are GNSS stations, because the amount of data which is transmitted is extremely small. So we have very low latency for those stations. But then when we start switching to seismic station, you see that we start having slightly higher latency. And then, yeah, of course, so that's the full list of station. When you click on the station name, you can go either through the station page that I will present later, or through the ticketing system, but I'll come back to that. You can also click on the station itself, and it will bring you to the station page. But that's not the only map we have. So that's the map about latency. So that's a real-time snapshot of the network. But sometimes it's interesting to look at more what we call data availability, which is the amount of data that was received from a station over the amount of data that was supposed to be received. So how much data did we really receive from that station over a period of time? Right now it's 24 hours, but you can select any time period, for example, 2 days, and that will tell you, okay, you can again sort out by data availability. You will see basically, so from all the stations in blue, that we receive at least 99% of the data we were supposed to receive over the last 2 days. You can decide to switch the timeline to 7 days. Yeah, and then you see, of course, the longer is the time period, the less 100% station there will be, because you will always lose a packet here and there. The station in the right are the stations that are currently down in general, and yeah, so you can go down this list, and you'll see so the station, and at the end I don't know what's going on. Oh, okay. And again, if you click on this station on the map or on the table, that will bring you to the station page. We have even further this concept of timely data availability, which is the same as data availability, but for the data to be taken into account, data has to arrive on time. So, which means for us, on time for the purpose of earthquake early warning. So that means within 5 seconds. If it doesn't arrive within 5 seconds, it will not be taken into account into the calculation. So that's why you see a little bit more station in yellow that maybe were blue previously, because the data would arrive, but maybe after 5 seconds. So again, you can zoom in, zoom out, look at specific stations, and see if you have some part of the networks that are affected or not. So there are many maps. One is about data quality. It's also interesting. That's the spectral level at 50 seconds. And so that only works for stations with broadband sensor right now. That's why you see many of the stations in gray in the Bay Area or Parkfield. In fact, they are geophone stations, so we don't compute that for those. And again, so for example, the more white it is, like for example here, or the station light blue here, it means the station is more noisy. And again, you can sort out the station by noise level. And that gives you an indication also about how good are the station. And of course, we target lower frequency, because that's usually a better indication of how good is the station in terms of data quality. But we also pull information from different databases, and in fact, one of them is SIS. So this interface sorry, I'm clicking. So this interface that has been developed by Caltech, and I think most of the regional seismic network now are putting all the metadata information from their station into that system. And so BATS is able to connect to that system and display information from there. One example is the type of sensor. I think that's very interesting to see the sensor distribution. In our case, we have a lot of STS sensors. I mean, one, of course, that's the oldest generation, 2.5, 5S7 are the more recent generation. Also a number of GROP, but more recently in green, a lot of MBB2s because all these sensors were purchased. So they are a little bit higher noise than the STS sensor or the grow-up sensor, but they were purchased in the framework of the rolling out of the earthquake early warning system. We only have one RefTech left, I think, here, and we have a few nanometric sensors that we have started to deploy throughout our network. Same with the digitizer types. So again, a lot of Q8 because those were purchased in the framework of earthquake early warning system, and same with telemetry. So different type of telemetry. Again, all this information is pulled from SIS, and with more and more red stations that have dual telemetry. And so it's not the perfect way of displaying it right now, but for dual telemetry, if you just hover with the mouse over the station, that will tell you that, for example, that station is connected both to cell modem and to PSC, which is the microwave network operated by the state of California. So I think that's all very useful information because very quickly you can switch from one map to another depending on what you're interested in. We have a last dashboard about mass positions. Again, so that's more for the team in charge of recentering the sensor to see which sensor might have mass position that are out of range, and then be able to target those stations in priority. So then you can select any of those maps. For example, we can come back to the latency and then zoom on any station. So for example, this station in the middle here, and by clicking on that station, that will bring you to the station page. That station page collects information from many different databases sources. For example, here you have basic information about the station that comes from SIS, a map. You have like some main metrics, timely data availability. For us, that's really the main metrics, how much data arrived on time over a certain time period. And again, all these metrics will adjust depending on the time period you select here, which is also very nice. So now it's the last 24 hours, but if you want to look over the last 2 days, you will see all these graphs, they immediately adjust to this time period. So, I mean, it was good. I click on that station, very good station, 100% data availability over the last 2 days. That's an indication of the core quality, the voltage at the station, perfect. Again, so we receive all the data and on time. That's data availability, timely availability over the last 2 days. Those are the mass positions. Those are the spectral level at 50 seconds, 1 second, and 10 Hertz. And again, so if you click on each of these graphs, it will bring you to a page with more information. For example, if we talk about data quality and you want to see more details here, that will bring you to a page where you see in time this spectral level at this 3 frequency that we discussed, 10 Hertz, 1 second, and 50 seconds. And again, you can select a different time period, for example, 2 days. You will zoom out. What you see here below is the waveform that are pulled out directly from our NCEDC, our data center archive. And you can see for the different channels, the waveform and the spectral level at the same time. So that's very useful. We have here information about our telemetry and the different networking hubs that the data is going through. Right now, we are working in trying to make this name a little bit more user-friendly, especially for the staff in our teams that are not part of our sysadmin team. But right now, it's just the IP addresses. But that's already, so all these different links here, you can see their performance over time, and that already give a good indication of how long it takes to transmit the data and what are the parts of the links where it takes the most time. We also have, like, again, L1Z, so latency plot here, and here some bars that indicate the performance of the power, communication, and digitizer over time. And again, by clicking on this, for example, if you would like to see how the power system is performing, so that's much more for the field engineers. For example, here, there is a lot of metrics that are being pulled out from the power system. Again, the possibility to zoom in on, okay, let's see, I think that's a solar system here. So 7 days. So you can see it's typically a solar system charging during the day. And you can see all these metrics that are being displayed as you scroll down. Same with, I show power. Maybe we can look at the radio network. Same thing, maybe over a longer time period, and with different parameters that are pulled out from the radio. So that's about the stations. Maybe we can stop here for the station. So now I'm going to go through other part of the system. We saw the network maps. We saw the specific information for the stations. We also like to monitor our acquisition system, and especially the data that we acquire from the different networks. So that's all the stations that are down now, but that we don't get data. Ooh, that's interesting. So that should not be gray. That's what's happening with a live demo. I don't know. When I did it, even just before the presentation this morning, you could see how long it takes to import data from these different network, and I add value. For example, those are the data from CGS, and that allows us when part of our network is down. Data quality, we monitor data quality per station, and we can look at the spectral level per station, but we also develop this plot, so it's a little bit more heavy. It takes a few seconds to load, but that gives you that kind of classify all the station by noise level. Again, you can select different time period, but here, you see like the station that are the most noisy. Again, you can select different frequency here, 1 Hz, 10 Hz, 50 seconds. And see what are the station with the highest noise and with the best station at the bottom. So that's also, especially for our data analysis team, a very good snapshot of the current noise level throughout the network. Let me close a few pages here. Maybe up. Come back here. The IT infrastructure, same thing. So this is being built right now, but the possibility to monitor all our servers, and so you can select different servers. You can also select different time period as always, and be able to look at, for example, the load, the memory usage, the disk usage, the ping, so the availability of the server. I'm looking at the time to see how much I can present as part of that presentation. So one thing I thought would be interesting for you today is ANSS metrics. We have developed quite a number of dashboards to monitor those performance metrics. I thought I would focus on two of them. One is for the reviewed origin. So now we have a new set of ANSS metrics that we have to meet, and we wanted to see how good we were at meeting those metrics. So that's the time to review an event. So you can see this green bar represent, like each of them represent an event, and so we have to review them within a median value of 15 minutes. And so basically, if we are below 15 minutes, the bar will be green. If we are slightly above yellow, and if we are above 20 minutes, the bar will become red. And that's very useful because now every time we, for example, in this bi-weekly NCSS call, where we meet with all our NCSS colleagues, we start those meetings with those pages just to review what has been our performance in terms of delivering these products to Comcast. On the right side, you see these two metrics that are the median and the 98th percentile for review origin, and you see that we are well within those metrics because I think that the threshold for the median is 15 minutes, and for the 98th percentile, I think it's 7 days, and right now we are at 15 minutes. We also have a map where those events are displayed, so when I use the map after I'll show you, but here in that table you also see how long it took, so it's more or less the same value as in this bar. But what's interesting is we pull the value at the same time from our internal system and also from Comcast, so we can compare and make sure that not only we produce those reviewed origins, but also that they are received in Comcast. And of course you can choose any time period, so now 30 days. It's more interesting when you take more days, so let's take 90 days. And you can see that now. I mean, should I scroll? Yeah, I will scroll down on the map. So, for example, here we had an event in red, and so that was very interesting because when we came up with that dashboard first, then we look at with our data analyst why it took so long to review that event at the time, and there are many different reasons for. There were others in the past as well. So, but usually it's always like split events. So the automatic system did not create two events, only one. So of course, when the second one was created, it was not created and reviewed on time. Another issue sometimes is that the magnitude is just below the threshold that this event should be reviewed within a short time frame. Maybe at the initial magnitude was 3.3 or 3.2, and you see here that it just reached 3.46, which is just above the 3.45 threshold, which is trigger an automatic reviewed origin to be reviewed within a short time frame. So I think that's very useful, and that allows us to not to wait for especially the ANSS management program to let us know whether we are meeting those metrics or not, but we can monitor that on a daily basis. Same with shake maps. So very similar graph for shake maps, making sure that we push those shake maps within an acceptable time frame with, again, the metrics for the reviewed, for the median and the 98th percentile, and the information we pull from both our internal system and Comcat. So that's for ANSS metrics, and we have more dashboards, but I thought that that will be most likely the two dashboards that you will be the most interested in. Something else that I can talk about also is a set of maps that I think I've already presented in different frameworks, but more for monitoring the performance of our earthquake early warning system. So in that case, we have maps that represent all the stations that contribute to the earthquake early warning system. So shake alert or queues for the California part from all the different networks. So in that case, it's not only the Berkeley station, but stations from all our partners, Caltech, CGS, the USGS, etc. Again, when you click on any of those stations, you will see which station it belongs to. So in that case, it's Nevada. And then clicking on that page, there will be a basic set of metrics display for, performance metrics, or let's say state of health information display for that site. And that's really a real-time snapshot of the network. So which means these maps, they are updated every 10 minutes. So if a station goes up, down, the color will change. You see that they are color-coded by latency. If the data arrives within 2 seconds, dark green. Between 2 and 5 seconds, we think it's still usable for earthquake early warning purposes. We don't have a lot of light green right now. Oh, there is one here with maybe a slower telemetry. And then if it starts getting orange, like here, it means data is probably a little bit too slow to be really usable for early warning alerts. And then if it's red, it means there is at least a 1 hour delay in getting the data, if not for the station to be completely down. So that's a current snapshot of the network, updated every 10 minutes. And what we wanted to know is, given the current status of that network, what will be the performance of the earthquake early warning system if there would be an earthquake right now at a certain location in the west coast of the US. And so for that, we develop a list of maps. The first map, for example, is we know that one of the main algorithm for earthquake early warning, EPIC, that is, I think in 99% of the case, the algorithm that triggers first, needs the detection at 4 stations. So what we are looking at on those maps is each, in fact, pixel on the map. For each pixel, we simulate an earthquake, and we look at how long it will take for the P wave produced by that earthquake to reach the 4 closest stations that needs to be operational and sending data within at least 5 seconds. And so we look at how long it will take for that wave to reach these 4 sites, And so that's a time in second that you see. And of course, you see that the color is much darker in the Bay Area or in the LA area, because that's an area, those are areas where we have very dense networks. So of course, it's taking a very short time for the P wave to reach 4 station. It takes a little bit more time in the more remote parts of California, because the network is less dense in those areas. So then the second step is, in addition to this time to reach the 4th station, now we add the time for the data to be transmitted from the station to the data center. And again, that's a real measurement. That's the average latency for each stations over the last 10 minutes. And also how long it takes in average to process and push an alert. And yeah, we also take into account packet length and some other details to make it a little bit more realistic. So you see that now the time, of course, is a little bit higher than before, because we take into account more steps in that process. Then the next step is how long it takes for the alert to be distributed to the public. So in addition to the previous map, we had the time that it takes in average for MyShake to deliver the alert to at least 50% of the users that needs to be alerted to. And again, so we see, depending on the region, the current status of the network, the current status of the telemetry, we get the alert sooner or later, depending on the regions. So that's good, but of course, we knew from the beginning that we wanted a denser network along the main faults, along the areas with higher hazards, and also in the area with very dense population. So now what we wanted to know is, given that it will take a certain time for an alert to be delivered to the public, how many people will not receive an alert on time? So how large will be this blind zone around the epicenter, and how many people live in that blind zone? So that's another map where we see that now. It means that if an earthquake would happen, so again, we generate earthquake at each of these locations, and for each location, we look, okay, if there would be an earthquake at this location, how many people will not receive an alert on time given the current status of the network? You see that, of course, the area with a very dense population, they are more towards the purple, because if there would be an earthquake, of course, under LA right now, even if we are super fast at alerting, in a few seconds, the S wave would have already propagated to a certain area where millions of people live. But again, it doesn't mean that LA will never be alerted on time. For example, if an earthquake would happen here, and that's why this area is dark blue, there will be time to issue an alert before the S wave reach LA, and this is why this area is dark blue here, because it means that all the metro area around will be alerted on time. We also wanted to take into account a little bit earthquake risk for different intensity level. We wanted to again, in order to focus on the priority areas for fixing stations that are potentially down, we wanted to see to maybe remove, again as an option, the area where there was less of a 2% probability to get an earthquake with a certain intensity, in that case intensity 8, that will be felt at this location over the next 50 years. So you see some areas, especially, for example, the metro area around Sacramento. And finally, having a map that combines the stations. And this map, again, we are trying to improve the display a little bit, but the idea was really to be able to prioritize the station maintenance actions. So you see, for example, we have like 2 stations right here. Most likely by fixing the station, there will be a much higher impact on alerting a large number of people on time than fixing some of the stations here in green in areas with very low population and where already a lot of stations are. I think I'm already at almost 40 minutes, so I'm going to stop. I'm going to switch back to the presentation, and maybe in 2 minutes, I also wanted to share with you a small project that we have started about categorizing probability density function using machine learning. The idea is that, as you saw through those dashboards, we monitor the spectral level at all our different sites, but that only gives part of the picture, and usually people that are really interested in data quality, they look at this PDF over the full spectra, because of course at a certain point of time you can always have a single frequency that increase because there is a truck or a car driving nearby the station. It doesn't mean that's a bad station, but whether when you have PDF of a longer time period, that's a much better indication, and also the full spectrum of data quality. Of course, that's currently really a manual process. So someone will have to look at this PDF one by one to see if we think the station is as good or bad data quality. You see typically an example of a very standard spectra PDF, and then typically a site where there is significant issues. So yes, we wanted to do a little bit better in terms of monitoring data quality, and we decided to start with broadband stations. So the input are those matrix you see here, 122 by 151, and start very easy. Okay, 0 good, 1 bad. So just 2 categories. First, we had to build a training data set. And of course, we didn't have to review all these PDF one by one to decide if they are good or bad. So we decided to use unsupervised learning algorithm first. And one very standard one is dbScan, which allow grouping all the close points together and identifying the outlier regions. So we did that over thousands of PDF, and then there was still for about, I think, 14,000 PDF, a manual review to make sure that at least the initial training data set was very accurate. So we had to adjust it a little. And then we had confidence in this training data set. And then we could categorize this PDF into 2 groups, bad on the left, good on the right. Once we had that, we injected that into a neural network. So, okay, we have this matrix, we flatten it in more than 18,000 points, and then we reduce it to 512, which is quite standard. We have 2 steps, and then at the end, we have a value which range between 0 and 1, and that gives you an indication of how likely is the PDF to be good or bad. I'm going very quickly through that. We put a lot of thinking and fine-tuning into that configuration, but just because I have only 1 minute or 2 left. The results, so as I said, this training data set was about 13,000 PDF that were at the end all reviewed manually. And then we get more than 98% accuracy. So we are very happy with that first algorithm or process that was developed. And the next steps now are to, first of all, re-inject those wrong identification for the PDS into the training data set, and then play again with those and try to improve the training. Try also, because we feel this is possible, to split in more categories than just 0 and 1, having maybe trying to identify, because in these outliers, they were in many different regions. So, maybe we could separate, in that case, the sensor clipped, in that case, it was digitizer noise, etc. Apply the similar process for strong motion data, and that would be the last step, try to trigger alerts when we identify byte quality over a certain time period at the station. So I think I'll stop here, and I'll give the floor back to you, Mary.